Hello, in this video I'll be solving A-level further maths complex numbers questions. I've decided to choose different types of questions that I see come up most often in actual A-level papers, and also to give you sort of some diversity in questions, some different types of complex numbers questions to make sure you're prepared not for everything, but for quite a lot. How I recommend you go through this video is I recommend that you see the question, you pause the video, you attempt it yourself, and then you see my solution. But if you just want to sit back, watch, passively learn, that's perfectly fine as well. Also, I highly recommend if you're unfamiliar with the topic or if you're unsure of your own knowledge of things, watch my complex numbers full guide video, maybe on 2 times speed. If you're finding it a little bit easier, skip around it, see what you know, see what you don't know. I think that if you watch that fully, you'll be fully equipped with everything you need to know in order to solve these questions. Cool. With all of that out of the way, let's get on with it. Question 1. Z cubed plus 32 plus 32i root 3 equals 0, giving you answers in the form of r equals to ei theta, r is greater than 0, r being the modulus, and the argument being between minus pi and pi. Cool. So firstly, let me just sort of put it into a better format so we can let's just try and visualize what's happening first. Right? So now this looks much more like the a plus or minus bi type complex number, right? It's much more standardized. Also, I highly recommend that if you get any complex number questions that's in the form of a plus minus bi, then you plot it on an Argand diagram. This really helps sort of visualize things and, will ensure that you don't mess up, especially in calculating the argument. So minus 32 minus 32 root 3. It's going to be roughly here in this quadrant, with this distance being 32 and this distance being 32 root 3, right? Okay. Let's call, this is going to be the actual argument, theta. Let's call this small angle here, what we're going to work out, alpha. Cool. So let's go based off this triangle that I've just drawn here and work out what the modulus and argument are of z cubed first, not z yet. So the modulus will be, right, modulus z cubed would be square root of 32 squared plus 32 squared, just Pythagoras for right angle triangle. This works out to be 64, perfect, right? Because 64 is a cube number. Therefore, the modulus of z is the cube root of 64, which is 4. Nice and easy. Okay, now let's try and work out what alpha is. So alpha is going to be inverse tan of 32 over 32 root 3, right? This is the same as inverse tan of 1 over root 3, which is either 30 degrees or pi over 6. I'll write it in radians because that's what the most further maths questions, if you see an angle, put it down in radians. Cool. So if this is pi over 6 over 30, that means this angle here is going to be 60, and we know this angle here is 180 or pi, the orange bit left, right? So remember, the argument of a complex number is always from the positive real line. So the theta is going to be pi plus 60, which is pi over 3. So pi plus pi over 3, which is 4 pi over 3. And because now we have a cubic number, so a cubic number will have 3 solutions, or 3 roots, right? So we'll just keep on adding 2 pi to this, which will give us... Oh, we also need to keep it within the range of minus pi and pi, right? And remember, this is also the solutions to z cubed. So what we'll do is, it will be over 9 in the end. It will be like 4 pi over 9, and then minus 2 pi over 3, and minus 8 pi over 3, right? So when this is, remember, argument of z cubed. So when we go to find the arguments of z, right? So the actual answers is going to be divided by 3, which is going to be 4 pi over 9 minus 2 pi over 9. And now this one will become in range, which is going to be minus 8 pi over 9. So, just to formally write the answer down in the modulus argument form as required here, I to I theta, we've already worked out the modulus, and these three are going to be the arguments. So it's going to be 4 to the e 4 pi over 9i and 4e to the minus 8 pi over 9i. Cool. So not too bad, just a very standard complex number question. Let's look at the next one. The complex number w is given by some fraction. Immediately I'm thinking rationalize the denominator, p is a constant. Express w in the form of a plus bi, again rationalized, where a and b are real constants. Give your answer in the simplest form in terms of p. Okay, so let me just do that on the right here. So part I of this question. Let's do it in a different color so that you know sort of what's what. We can do it in a light blue. Cool. So part I. So rationalizing just means that you use the complex conjugate and multiply both the numerator and the denominator of the complex conjugate of the denominator of the actual thing. So it's going to be times 2 plus 3i times 2 plus 3i. And why that is because now the denominator becomes the difference of two squares. So let's multiply out the numerator. So it's going to be 2p plus 3pi minus 8i, and then minus 12i squared, which is just plus 12, right? Over 2 squared minus 3i squared. Now this will give us 2p plus 12 minus, or sort of plus 3p minus 8i in the numerator, and the denominator will be nothing but 4 minus 9i squared, which is just in the form of a, just splitting the fractions, splitting the numerator up. 2p plus 12 over 4 plus 9, this will become 13, right? Plus 3p minus 8 over 13i, right? So that's just going to be the answer of part A. Part B. Given that the argument of w is pi over 4, find the value of p. Okay, so if we were just given a complex number a plus bi, how you find the argument is you do the inverse tan, like we've done sort of in part 1, the inverse tan of the y, or the x over the y, right? And they've told us the argument is pi over 4. If you remember closely, tan of pi over 4 or tan of 45 is actually just 1. What that means is that the x, or the x in this case, which is the a, the real part, and the imaginary part have to be the same. So what this tells us is that this part, which is the real, equals this part, which is the imaginary, right? So for part B, we can just solve for p using 2p plus 12 over 13, equals 3p minus 8 over 13, right? 13 cancel out. This just gives us p equals 20 once you simplify the numerator. So that's what p is. P is 20. If I'm going too fast, if you don't understand anything, sort of, firstly, if you're missing out on the concepts, watch my full guide video. If not, I'll drop my email in the description. I'm happy to sort of walk through this question or another that you might have in complex numbers privately with you on a call or something. So please feel free to reach out if you're really, really struggling. Okay, let's attempt part 2 of the question. Let me make this a bit smaller. Actually, let me get this out of the way. So let me put part B like here. Done and over with. Okay. Part 2. Complex number z is given by z equals 1 plus lambda I 4 plus 3i. So this is multiplying two complex numbers together. Lambda is a real constant given that the modulus of z is 45. Find the possible values of lambda. Cool. So the cool thing is that when you multiply two complex numbers, remember this can be written in the form of r e to the I theta, right? So imagine that both these complex numbers were written in this form. The modulus of the result will be nothing but the modulus of this one multiplied by the modulus of this one, right? So we can use that fact to our advantage to say that the modulus of the result, which is z, is just going to be the product of the modulus of the first one, which is going to be 1 squared plus lambda squared, times the modulus of the second one, which is going to be 4 squared plus 3 squared. 45, right? So we can sort of take this under one common square root. So we can do root of 1 squared plus lambda squared plus, oh sorry, times by 4 squared plus 3 squared equals 45, right? This means that 1 plus lambda squared times by 25 equals 45 squared. 16 plus 9, 25. Cool. So 1 plus lambda squared equals 45 squared over 25. Which means that lambda squared equals, or lambda squared plus 1, do that on my calculator. Oh no. So lambda squared plus 1 equals 81, which means that lambda squared equals 80. Oh, if they just left at 81, we could have had nice answers, but no. So lambda equals plus or minus, because we have to square root, 80. Does anything go into it? Yeah, 16, right? This is the same as, so you can take 4 out. So 4 root 5. Plus or minus 4 root 5. Yeah, so the hint is find the possible values. So they want you. If you don't put the plus or minus there, they will deduct marks. So make sure you put plus or minus either root 80 or 4 root 5. Cool. Let's try sort of another general complex number question, and then we'll move on to some more De Moivre theorems, roots of unity, and so on and so forth, more difficult questions. Given that 4 and 2i minus 3 are roots of the equation, x cubed plus ax squared plus bx minus 52 equals 0, where a and b are real constants. This is again a very common type of question. So what they're expecting you to know here is that x cubed will have 3 solutions. They clearly have one real solution, real, right? One imaginary solution. If you watch the video, you know that imaginary solutions are never alone. They always come in pairs, and the pairs are always complex conjugates. So, pause the video right here and think about, based on these two things, what the third root could be. Now, if you've just said the third root is so obviously 2i plus 3, then you're dead wrong. You're dead wrong. It does look like it's that, but remember, it's always a plus bi, right? And a minus bi. Here they've put the imaginary part at the start. We always only flip, in conjugates, we flip the imaginary part. So I'm assuming this is where like a lot of people might go wrong, and then you'll have to carry that through to part B to find A and B, and you'll mess up the whole question. But the correct third solution, the correct answer to part A, is minus 2i minus 3. So find the values of A and B. Now this is again very common, right? What they want you to do is, so for example, if you get the roots of a quadratic, right? You know that x minus a and x minus b equals the quadratic if a and b are roots. This is called the factor theorem, I think. And you can just use that and say that because you know the root, because you know 4, 2i minus 3 and minus 2i minus 3 are roots, you know that x minus 4, comma, x minus 2i minus 3 and x minus 2i minus 3 are all going to be factors of this cubic. Now what this means is if I just replace the commas with multiplication sign, this will for sure lead us back to our cubic. So let me expand out the imaginary things first. So it's x minus 4 times x minus 2i plus 3 and x plus 2i plus 3, right? So it's x minus 4 with x squared minus 2xi, plus 2xi, and then plus 3x minus 2xi. So minus 4i squared, which is just plus 4, and then minus 6i plus 3x plus 6i plus 9. Okay, so minus 6i and plus 6i cancel out, 2xi cancel out. So we're left with x minus 4, x squared plus 6x plus 9, right? And if we expand this out once more, we get x cubed plus 6x squared plus 9x minus 4x squared minus 24x minus 36, right? Which will give us x cubed plus 2x squared minus 11x minus 36. So in this case, wait, it shouldn't be minus 36 then. Interesting, have I gone wrong somewhere? Oh, of course, plus 4, so it's actually plus 13. Right, this is minus 52. Cool. So A in this case equals 2 and B is minus 11. If you messed up on this part and thought that the complex conjugate was 2i plus 3, then you get part B wrong as well. Remember, the complex conjugate is you always flip the sign of the imaginary part, even if the imaginary part is at the start, like it is in this question. Cool. Now, let's move on to Demoivre's question. Demoivre's? I don't know how to pronounce it. Don't quote my pronunciation. I'm here to teach you how it works, not to teach you how to say it. So, sine 7 theta, we have to prove that sine 7 theta equals 7 sine theta minus 56 sine cube theta, 112 sine 5 theta, and so on and so forth. So this is a very standard question, which typically requires a lot of working, and I'm sure this one's going to be the same thing. So the traditional way to sort of approach this is that you say that, right, z, or like a normal complex number, equals cos theta plus I sine theta, right? So z to the power of 7 will equal to cos theta plus I sine theta to the power of 7, right? So let's expand this cos theta plus I sine theta to the power of 7. There's two ways of doing this. I'll teach you both. So this is just a binomial expansion. The first term is obviously going to be cos 7 theta. Actually, let's make a key. So cos equals C and sine equals S. Because I can't be asked to write cos and sine every time. It's going to be a lot of them. So C7 theta, right? Plus C6. I'm not even going to write theta. C7, C6, right? This is going to be, the coefficient is going to be 7 choose 1. If you've done binomial expansion, you know what I mean. So 7 choose 1, you can calculate it on your calculator. It's the C button. It's the C button. If you've got the white calculator like me, this one, it is the NCR just over your divide button. I don't know how well you can see that, but you can just do 7 choose 1 to get the coefficient for binomial extensions. And then you reduce the power, so the powers of sine are going 0, 1, 2, 3, 4. The powers of cos are going 7, 6, 1, 3, right? Sine 1, so it's I sine 1, sine I, right? and then plus 7 choose 2, c5, sine squared, so it's actually going to be minus, because I squared is minus, and sine squared, and so on and so forth. Now, for some reason or another, if you want to do this without a calculator, I don't see why you would, but I find myself doing this sometimes when it's not 7, but it's a lower one. You can use this Fibonacci's triangle. So 1, 1, 1, 2, 1, 1, 3, 3, 1. How you get each... Sorry, my laptop died, so the video recording stopped halfway through. So, carrying on, I was just talking about the Fibonacci triangle, right? So you can do 1, 1, 1, 1, 2, 1. You calculate each number by adding up the previous. So this number will be the sum of these two. This number will be the sum of these two. This number will be the sum. So essentially, the two that are directly above it, you sum them, and then that's how you get the next one. Why this is relevant, I will let you know. Let me just move this key like here from this. So the next one is going to be 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, right? And 1, 7, 21, 35, 35, 21, 7, 1. So essentially, why this is relevant is because these are all the coefficients in every single binomial expansion. If it's like a plus b to the power of 6, then all of the coefficients for all of the terms will be in this row. So in this case, because it's to the power of 7, all of the coefficients that we find will be from this row. Whereas using this, I can sort of speed up the process of doing this, right? So I can just do, it's going to be cos 7 plus 7 cos 6 sine I, right, minus 21 cos 5 sine squared, again, minus 35 cos 4 sine cubed, I comes back, and this one the minus is going to go away, 35 cos 3 sine to the 4, because it's I squared, 2I squared, it's minus 1, cancelled out. Plus 21 cos squared sine 5, I again. Then minus, because it's going to be I squared now, 7 cos sine 6. And lastly, it's going to be minus again, just sine 7i, right? So we're looking for what sine is going to be, and if you notice here, sine has an I in front of it, right? So we only really care about the imaginary part of this, right? That's going to be 7 cos 6 sine. So this term, this term, this term, and the last term. Minus 35 cos 4 sine 3i plus 21 cos squared sine to the 5i minus sine to the 7i. Cool. If you notice here, there's only sines in this, there's no causes, which means that we need to use the identity that cos squared plus sine squared equals 1. Therefore, cos squared equals 1 minus sine squared. Right? Inserting that into here, I'm going to just carry on here. There's more space. Cool. We get 7, 1 minus sine squared cubed, because that's cos squared cubed. Sine theta again, minus 35 cos 4, right? So it's going to be 1 minus sine squared squared sine to the 3, and then plus 21 1 minus sine squared sine to the 5, and then minus sine to the 7. Cool. I'm not going to expand all this out purely to save you and me some time, but I'm sure if you do expand this out, you'll end up with an expression that looks just like that. So That's how you're going to do part A of the question. Remember, it's always like this. Just assume this, expand the brackets out. For cos, it's going to be the real part. For sine, it's going to be the imaginary part. Use the identity that cos squared plus sine squared equals 1 to substitute it into here to get an expression that only has sine in it. Remove all cos from it. Okay. Hence, find the distinct roots of this equation. Cool. So, I don't have much space. I'll briefly show you guys, maybe here, how to do it. Let's draw a line. Let's use orange as well, why not? So, as you can see here, right, it looks very familiar. 7, 7. So, essentially here, we use the substitution x equals sine theta. As you can see, from part A to part B, there's a clear direct connection. So, there's just a +1 at the start of it. So essentially, it is nothing but 1 plus sine of 7 theta equals 0. X equals sine theta, sine 7 theta, yeah? So sine of 7 theta equals -1. Now, as we know, we can just do sine inverse -1. It becomes a very standard trig question. Right? So essentially, 7 theta will equal to minus pi over 2 and so on and so forth. So theta will equal to minus pi over 14, right? And it's asking us, giving us 3 decimal places, what are the roots of the equation? To solve for x, right, you'll have to do this 7 times. Just find 7 of these roots repeated, wherever sine theta is equals to -1. So x equals sine theta. Let's bring this back, right? So one solution, or the first solution for x is going to be x equals sine of minus pi over 14, which is equal to minus 0.223, because it's set to 3 decimal places. And obviously you do this for all 7 roots, because there's going to be 7 roots as is to the power of 7. But yeah, in simple terms, that's how you do part B. If you're completely stuck as to how to do part B, think about how can I use everything I've done for part A. It's normally a lead-up question. This is just some exam technique advice, essentially. Okay. 1 second, let me blow my nose. Sorry, by the way, if my sniffling's been annoying you guys. I'm ill currently. But I still thought I'd get this video out. Cool. So the modulus of z is greater than 1. So as you can see, this is a roots unity question immediately, right? So write down the sum of the infinite series. It doesn't even have anything to do with the roots of infinity. This is straight up in your formula booklet. So the sum of an infinite series is just a over 1 minus r, right? Which in this case is just 1 over 1 minus z, where r is the common difference between the terms. Okay, so part B, given that z equals half cos theta plus I sine theta, use the answer to part A. So use the answer to part A and De Moivre's theorem, or otherwise to prove that blah 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 equals 2 sine theta over 5 minus 4 cos theta. Okay. So, why have they said using the answer to part A? It's sum to infinity series. As you can see, it's 1 plus z squared, right? So, I already see it, z squared. So, it's like 1, z squared, z cubed, and so on, right? So, if I had to write it as such, 1 plus z squared, where z is this, plus z cubed, and so on, right? This looks like 1 plus half cos theta plus I sine theta, right? Plus a half cos theta plus I sine theta all squared, right? And so on and so forth. What this looks like is 1 plus half cos theta plus I sine theta plus it's going to be a quarter, and then because of De Moivre's theorem, it's going to be cos 2 theta plus I sine 2 theta, and so on and so forth. So as you can already see, we're sort of getting there, right? Half sine theta, half sine theta, a quarter sine theta, quarter sine theta. So it's clearly going to be the imaginary part, right? The imaginary part of this, 1 plus the imaginary part of this. So using what we found here, the sum of this infinite series, right, is going to be nothing but 1 plus the sum of the imaginary part is infinite series, right? So the imaginary part of 1 over 1 minus z, which is 1 minus half cos theta plus I sine theta, right? So far so good. So just solving this for now, essentially, this will give us 1 over, or let me bring the 2 up actually, 2 over, this will be a 2 minus cos, I don't know what cos squared is, cos theta, right, plus I sine theta. So I is in the bottom, I'll have to rationalize this. So times this by 2 minus cos theta minus I sine theta over 2 minus cos theta minus I sine theta, right? Okay, let's carry this on over here. So this gives you, in the numerator firstly, it will give you 4 minus 2 cos theta minus 2 sine theta I. I'm already liking what I'm seeing in the numerator. Look, 2 sine theta all over 2 minus cos theta squared minus I sine theta squared, right? So first skin on this. So 4 minus 2 cos theta minus 2 sine theta I over 4 minus or plus cos squared theta minus 4 cos theta, right? And then the I squared becomes plus. So plus sine squared theta, right? So cos squared theta plus sine squared theta is 1. So the denominator we get, the real part, let me just split this into real, right? 4 minus 2 cos theta over 5 minus 4 cos theta, right? Plus 2 sine theta over 4, 5 minus 4 cos theta. I, imaginary part. Cool. 2 sine theta, 5 minus 4 cos theta. 2 sine theta, 5 minus 4 cos theta. So hence proven. Okay. Show that the sum of the infinite series cannot be purely imaginary. Okay, so it cannot be purely imaginary. So therefore, the real part cannot equal to 0. Right? That's all that means. So what was a real part again? Real part this, right? So hypothetically, for part C, what you do is you try setting this to 0, I think. 2 cos theta over 5 minus 4 cos theta equals 0, right? This will lead to 4 minus 2 cos theta equals 0. Oh yeah, this means that 2 minus cos theta equals 0, which values to cos theta equals 2, which is impossible. Why? Because cos theta lies between minus 1 and 1, right? So cos theta can't be 2. Therefore, the real part of this equation, this is the real part, right? The real part cannot equal 0. So you have to have a real part. So it cannot be purely imaginary. This thing. Cool. Moving on to the last question for the day. Point P. One second, I can't hear you. A moment. How's it going? Oh yeah, that feels better. Cool. So the point P is one vertex of a regular pentagon in an Argand diagram. Center of the pentagon is at the origin. P represents complex number 6 plus 6i. Determine the complex number that represent the other vertices of the pentagon in the modular form. Oh, I'm not sure why this is 5 marks. This seems to be not too bad of a question. So if I had to quickly plot it on the Argand diagram, 6 plus 6i, right, will be like straight up here somewhere, right? The argument will always be 45 degrees because it's like a straight, it's like exactly halfway. X equals y, right? It lies on the line x equals y, or pi by 4, which is the argument. And the modulus, so the modulus is going to be, so r equals 6 squared plus 6 squared, which is just going to be 6 root 2. And arg would equal to, or theta, let's call it, pi over 4. And because it's going to be a regular pentagon, that means you split 2 pi into 5 equal segments, right? So you will just add 2 pi plus 5 to get the next angles, right? So this will give you pi over 4, and then the next vertices are going to be, it's going to be 20, 5 pi plus 8 pi, right? So 13 pi over 20, and then you keep on adding 8 pi to this, so 21. Does it want me, it doesn't really specify what range it wants the argument at, so we can just do 21 pi over 20, and then it's going to be 29 pi over 20, then it's going to be 37 pi over 20. That's the 5 vertices. Cool. Then it's going to go back to pi over 4. So the official answers for this question, right, the other vertices, so we already have this one, are going to be 6 root 2 e to the 13 pi over 20i, comma 6 root 2, and then this one, 6 root 2, this one, 6 root 2, and you get the picture. I won't write them all out. But that's going to be the solutions. That's not too bad for a 5 marker, I have to say. Like, I've seen way worse. So if you get that on the exam, like, you should be chilling. So part 2. Part 2a. On a single Argand diagram, shade the region R that satisfies both. Okay, so this loci is going to be a circle. It's in the circle format. And this is going to be 2 half lines, right? So the first one is going to be, oh wait, let me draw straighter. The first one's going to be a circle centered at, it's going to be minus, right? So you flip the sign inside, so it's going to be plus 2 at center, and the radius is 2, so it's going to touch the origin. So because it's greater than or equal to, we're drawing a solid line. But if it was strictly greater than, then we draw dotted lines. Not greater than, less than, I meant, sorry. Right? This is 0. What happened? This is 0. This is 4. Cool. And pi over 4 is just 45 degrees, something like this, right? Pi over 4. And pi over 3 is 60 degrees. It's going to be something like this. So the shaded area is going to be here. It's my highlighter. Yeah. And that should be your answer. Again, I've just drawn a rough sketch. Like, they haven't said sketch, but I'm assuming in the actual exam you'll be given some sort of paper. Use a protractor if you have one. Be extra precise, be extra specific, because they haven't specifically mentioned the word sketch. But again, it's also only a 2 marker, so I think you'll be alright. I think this should be fine. Okay. Determine the exact area of R. Cool. Oh, actually, I've got a nice trick up my sleeve to do this. So if you've already covered polar coordinates, if you haven't, I'll make a full guide on it at some point. But essentially, this circle looks awfully like the polar coordinate r equals sine theta. Or to be very specific, it's r equals 4 sine theta. Because r equals sine theta is just a circle that goes through 1, 0, but just going through 4, 0. Or 0, 4, sorry. Right? So I can just apply like the polar area formula, or the how to find the polar area between two angles. So how that works is, so you do area of graph equals the integral, so half times the integral between the ranges of pi over 4 and pi over 3 of r squared, which is 4 sine theta squared. So this will give you a half pi over 4 pi over 3 16 sine squared theta, which is 8 pi over 4 pi over 3, right? Sine squared theta. Now, the trick to integrating sine squared theta is that you have to realize you use the cos double angle formula. So cos 2 theta actually equals cos theta minus sine squared theta, right? So if you want to know what sine squared theta is by itself, you do cos 2 theta equals 1 minus sine, or 1 minus 2 sine squared theta, right? Therefore, cos 2 theta, sorry, or sine squared theta will equal 1 minus cos 2 theta over 2. Right? So this integration becomes 8 pi over 3 pi over 4, right? A half minus cos 2 theta over 2. So this just becomes d theta, sorry, this entire time. D theta, d theta, d theta. Right? So 8, and then times by a half theta, pi over 4, pi over 3, right? And then this will become minus cos 2 theta will integrate to sine 2 theta divided by 2, so this becomes divided by 4, pi over 4 pi over 3, right? And then you can just work all this out. Or to be fair, you could just do this on your calculator as well. I'm pretty sure excuse me. Yeah. You could do this full integration on your calculator and probably be fine and get the answer. So what the final answer comes out to be in this case is pi over 3 minus root 3 plus 2. So yeah, that was me basically doing different types of complex numbers questions to give you more exposure to the style of questions that they expect you to solve. I hope this video was helpful. Please watch the complex numbers full guide just for revision in case you haven't already. And yeah, stay tuned for more videos like this to come up on the channel. Thank you for watching. Bye. But while editing, I do realize that I've been sniffling the entire video, and it does get pretty annoying. I hope you forgive me. I am ill. I hope you still get loads of value out of this video. And yeah, comment down below what topic would you like me to cover next. But yeah, hope you enjoy watching the video. Thank you.